Hello everyone, my name is Jia-Jun. I'm a postdoctoral researcher at the Singapore MIT Alliance for Research and Technology. CollabCoder is a project I developed when I was a PhD student at the Singapore University of Technology and Design, in collaboration with my colleagues from the University of Notre Dame. Qualitative analysis is widely used in various fields, including human-computer interaction, psychology, social science, and educational research, etc. Through a series of data abstraction processes, such as coding, it transforms unstructured data into meaningful categories, themes, and even theories. Quantitative theory and the semantic analysis are the two primary theoretical methods employed in this process. These methods aim to achieve two main goals: rigorous and in-depth data interpretation through systematic coding, often conducted by a team of 2 or 3 researchers or even more. However, adhering strictly to the coding workflow in collaborative qualitative analysis poses significant challenges due to its inherent complexity and the time and labor costs involved. Firstly, the CQA process itself is complex. For instance, while CQA requires coders to independently perform open coding, it also needs data sharing and discussion based on that data. This transition cannot be facilitated by current tools like Atlas TI and MaxQDA, forcing them to revert to manual coding using Excel or Google Sheet, which offer more customization to meet the rigor requirement. However, this manual approach is time-consuming and labor-intensive. The entire CQA process involves multiple rounds of manual coding and iterative discussion, coupled with tasks like uploading, data sharing, and downloading. Unfortunately, existing coding software is not designed to accommodate this need. This mismatch between the process and available tools could potentially lead to incorrect or suboptimal CQA practices. Therefore, two crucial questions arise. Can we design a theory-driven system to simplify this process? Can we leverage large language models to decrease the time and labor cost? To answer our questions, we conducted a 3-step exploration to sharpen our ideas and design goals. Firstly, through a semi-systematic literature review, we have further narrowed down the focus of our idea. We have found that currently no existing tools are specifically tailored for the CQA process based on the ground-up theory and the semantic analysis methods. The review also found that LLM has been applied to quantitative analysis, but more emphasis on deductive coding. Therefore, we have decided to concentrate our efforts on inductive collaborative qualitative analysis, with a particular emphasis on the consensus building process. More specifically, we identified the key phases of the inductive CQA process, inputs and outputs, and practical considerations for each phase, which informing our initial design goals from design goal 1 to design goal 7. Secondly, through an examination of prevalent CQA platforms, we got insights into their essential features, pros and cons, refining two goals and generating two new ones. This step also made us propose a primary version of CollabCoder. Lastly, through the preliminary interviews with experts, we collected the insights into CollabCoder's workflow, features, and scope, refining two more goals. In total, we have 8 key design goals. The name of few, design goal 1, supporting key CQA phases to encourage stricter adherence to standard CQA processes, supporting varying levels of coding independence at each CQA stage, to ensure a strict workflow. Design goal 6, facilitating deeper and higher quality discussion. Through these design goals, we have proposed the CollabCoder workflow and implemented it as a web-based application, featuring a 3-phase interface that corresponds to the 3 key phases in the workflow. Suppose 2 coders, Alice and Bob, are conducting inductive qualitative analysis. Prior to the formal coding process, CollabCoder will split the text data into different units. Once the data becomes sentence or paragraph, Alice can involve Bob to join the project. In phase 1, independent open coding, Alice and Bob then independently code these units, adding their initial open codes. They can also leverage GPT to obtain code suggestions during the coding. This interface is an individual workspace for Alice and Bob, meaning that they cannot see each other's codes. When Alice adds codes, she can first quickly read the text and click on a cell and input her own code. After a short time, CollabCoder will suggest 2 kinds of suggestions, including ChatGPT suggested codes and relevant codes from the codebook. Alice can choose a code and edit it as needed. She can then add keywords as support. Keywords support will be shown beside the code. She can then add her certainty level between 1 to 5 and edit the individual codebook as needed. In phase 2, merge and discuss. The open codes proposed by Alice and Bob in phase 1 are paired together. The two coders discuss and compare their paired code over multiple rounds. This iterative discussion allows them to arrive at an agreed-on list of final code decisions. Phase 2 is a shared workspace for in-depth discussion, and the LLM can be group recommender. To access each other's codes, two coders must both have completed 100% of their tasks. All information are listed side by side, including original data, certainty level, keyword support, as well as original code. CollabCoder supports one-click calculation of similarity and interoperability. By examining the similarity of code pairs, they can filter the agreements and disagreements quickly. Two coders can start discussion and propose a code based on their coding information. If Alice and Bob cannot agree on with each other, they can request a suggestion from GPT, which will provide 3 alternative final codes based on the original code and text. After generating a final code decision, the two coders can replace the original codes, leading to updated similarity and higher interoperability. In phase 3, code group generation, Alice and Bob collaborated to organize and structure the final code decisions from phase 2. Through further discussion, they form cohesive code groups, which make up the complete codebook. Phase 3 is also a shared workspace. The final code decisions will be listed on the interface. Users can create code groups by GPT and do further editing. They can remove codes from group, drag new codes into the group. They can also generate a code group from scratch, drag the codes into the new group. To evaluate our system and compare it with the existing tool, Atlas TI Web, they designed a vision subject design involving 16 participants with varying levels of qualitative analysis experience, from beginners to experts. These participants were randomly grouped into 8 pairs. Before the study, we conducted a training session for all participants to ensure proficient in using our system. During the study, they performed 2 collaborative qualitative coding tasks on an Amazon book review dataset, using Atlas TI Web and CollabCoder respectively, within approximately 3 hours. Each task involved independent open coding, discussion to reach agreement, and the formation of a final codebook. Afterwards, we used the semantic analysis to examine the post-study interview data. Our results revealed 5 key findings regarding CollabCoder's effectiveness. Firstly, participants report lower learning curve. With CollabCoder, they perceived the system as easier to understand, more straightforward, and beginner-friendly. The GPT-assisted suggestion seemed to reduce their cognitive burden by providing helpful references. Even more interesting, we observed an intriguing group dynamic. This included follower-leader patterns, where one coder consistently followed the other's opinions, amicable cooperation patterns, where coders respectively discussed but sometimes struggled to make decisions due to a lack of dominance, and swift but less cautious collaboration, where analysis was completed quickly but with potentially less attention to detail. Our user questionnaire also revealed that overall participants found the CollabCoder more efficient for code generation, final code group creation, and disagreement identification. Additionally, a larger proportion of users agreed that CollabCoder is user-friendly and can be learned quickly. However, an interesting outlier emerged. Participants P6 with an expert consistently assigned the CollabCoder the lowest scores. P6 specifically mentioned that picking nuances from the text itself was a fun aspect of the coding process. He felt that the GPT suggestions made him feel like the coding was done for him, and he just had to apply it. Our findings indicate that the CollabCoder, compared to Atlas TI, facilitated significantly longer discussions among users. This resulted in a greater number of codes being discussed and ultimately led to higher interoperability. Overall, our work suggested that effective coding tools should be designed with workflows that align with established theories, while also enriching users' understanding of those theories. Furthermore, large language models could act as suggestion provider to aid the coding process rather than replacing human judgment. Additionally, LLMs can be valuable mediators, facilitating group discussions and code organization. The main takeaway of this research are 3 parts. First, the 8 design goals identified through an exploratory process. These goals informed the development of the CollabCoder workflow and its web application, specifically to facilitate the key phases of inductive collaborative qualitative analysis. and consensus building. Finally, this work provided valuable insights into the role of GPT suggestions within the collaborative qualitative analysis process. Please check our paper for more details at CHI 2024. So stay updated on the latest developments of CollabCoder, scan the QR code, and visit our website.